Welcome, I'm Ray Leipold. I'm the treatment plant supervisor here at the Hayden Bridge Filtration Plant. And I'm going to take you through a little tour of the facility here, give you a general overview of the overall operation first, and then we'll be jumping around trying to hit all the spots that I talked about here first and hopefully put them all together for you. So this is our diagram of the facility. We're rated for 88 million gallons a day of drinking water to City of Eugene. In the wintertime right now, we're flowing at about 17 million gallons a day, and our peak flow this last summer was really close to 50 million gallons a day. We bring our water in, of course, from the McKenzie River. Right down below Hayden Bridge on Marcola Road is our intake structure that's depicted here. Inside that structure we have 7 pumps that can bring in 125 million gallons a day. In the river are some fish screens that keep fish out of those pumps, but still allow the water to be pumped up through our transmission mains. From the pumps, we have 2 transmission mains that come up to the facility. One's a 36-inch main and one's a 42-inch main. And as they come up through, our first process step is the carbon feed building. And what we use there is called a powder activated carbon, which absorbs, not absorbs, but adsorbs different constituents in the water. What we use it for mainly is taste and odor, algae sources, hazardous algae bloom toxins, and just recently, of course, response to the Holiday Farm fire and some of the different materials that are coming down, which we don't know all the origin of those materials. So we put that in the water, it grabs a hold of those materials, and it's filtered out later in the process. As we come up past the carbon building, we have in the front yard here, I'll call it, we have some valves and some chemical addition vaults. And there we can add aluminum sulfate, which is our coagulant that binds together all the dirt and materials so they can settle out in our basins. And we can add chlorine there, and we can add a pH adjustment of sodium hydroxide. We're not doing that currently. Those are episodic use. And then after we add these chemicals, the next step in the process coming up through the basins here is kind of a mechanical flocculation where it stirs the water and those chemicals together hydraulically, very slowly, and it comes through a perforated wall that allows the water to run across here very slowly, and hopefully those materials settle out into the bottom of the basin here, which then later we can clean out and send to the ponds through that piping system. After the settling process, we have a filtration process that is a sand media and an anthracite coal media, 10 inches of sand, and then 18 inches of anthracite coal on top of that. We're not adding chlorine through here, so our filters now are becoming biologically active, so we use them as biological filters. That can help with things like toxins as well. It reduces algae. It can also take out some other constituents, dissolved organic matter. Then after the filters, it drops into a clear well underneath the filters, and then the water is conveyed to our 15 million gallon reservoir in the back of the facility. This is where we do another chemical addition here. This is where we do pH adjustment with sodium hydroxide to a target of 7.9 pH. And then the chemical sodium hypochlorite or chlorine we use to disinfect. We get our disinfection across here, or kill time CT across the 15 million gallon reservoir. And then again, we have pumps at the back end that pump to town, another 7 pumps that can pump about 125 million gallons a day. Convey it to the city of Eugene through 2 pipes, a 45-inch and a 60-inch transmission main. The transmission main goes all the way to our headquarters, kind of branches out at I-5 at what we call an intertime monitoring station. We have a station that monitors water quality, and by doing that we can also get credit for disinfection in these pipes between this reservoir and the 3 miles to I-5. And that is essentially the process. I guess the one part that I skipped here is the backwash process, where when we backwash the filters and they become clogged with materials, the backwash goes down to the ponds. When we bring the filters back online, initially it is off-spec water. We call it filter to waste, and we waste that to a tank and then recycle it through the facility. That's essentially the process. So I'd like to take you through each step, probably starting out at the sodium hypochlorite generation facilities, brand new, just put online in December of 2019. So we've had it for about a year now. And then we'll be going through the lab after that, which is brand new. About a week ago, we were able to move in there. Then we'll progress on through the facility. Sure, most of what has happened, especially immediately, was just an influx of organic matter, a lot of dissolved organic matter that we aren't really used to handling here. So we're used to the turbidity, which is kind of the larger particles, but we don't usually get that dissolved matter. And so we did have a spike in that, and then we had some taste and odor concerns that came along with that, kind of smoky taste, that kind of thing. And so that's where our powder activated carbon came in to take care of those concerns. As far as other things we've seen in sampling we've done, we do have an increase in metals, of specifically aluminum. We've seen an increase in, and barium. Those are starting to taper off along with the organic load, so we've had a few flushes now. So it's kind of made it through the system. It's starting to decline along with the organic matter. And so we're thinking that the new normal is, we haven't gotten there yet. We're still tapering off. The good news about all these things is, we take a before and then after sample analysis. So our treatment process is taking care of these things. So, whatever's coming in, it's not coming out. We're still delivering the same quality water that we were before. Right, so yes, we are still trying to make our biofiltration work here. One of the unfortunate things is when we turn on our pack, it takes away a lot of the food and absorbs it that our bacteria would be using in our filters, our biologically active filters. So right now we really have low biological activity in our filters, so it's more of just plain old filtration, and the heavy lifting is being done by our powder activated carbon. What we're going to be looking at moving forward with biofiltration is we're going to look at using a GAC filter media, which is granular activated carbon. So we're feeding powder right now up front, but there's also a possibility that we can use granular media in the filters in its place. And so we're going to investigate that with our pilot filter system. And we're working with the University of Toronto on these pilot projects. The University of Toronto is well known in the world for their biofiltration studies. They have 7 filter plants in the Great Lakes that they do biofiltration on. So we're working with them, and they're kind of guiding us through these processes. But for right now, we expect that we'll be able to stop feeding the pack here in the next month or so. is what we're anticipating. And then our biological activity will come back on our filters, and then hopefully moving forward with presumably how hazardous algae blooms because of all these nutrients that are in the water. Hopefully we'll be able to, in our pilot study how that GAC can also help us with the biological filters and the hazardous algae toxins. So long answer, but does that make sense? All right, so we're going to be entering our sodium hypochlorite building here. What we're doing here is a new process for EWEB. We're taking salt and we're doing an ion exchange and turning it into chlorine or bleach. It's a 0.8% concentration. So we used to have a gas chlorine system here, and it was very dangerous, hazardous material, and it was hard to get, so there's only one supplier here on the West Coast. So we did a study on what would be our next step going to disinfection, and we did a triple bottom line study, and what came out of that was that we should move to a sodium hypochlorite generation system. We can keep about 3 months worth of salt on hand. With gas, we had about 3 weeks worth in the summer. And so this helps us be more resilient because we can have more suppliers, we can keep more on site. So if we have some kind of emergency, we have our disinfection that we need to complete our process. So we'll be going in here. It's going to be a little bit noisy. What you're going to see is the generation system, which is taking a brine from the salt silos. So the salt is blown into these silos, and there's water filled up about halfway, and that water in the bottom is a brine solution. It's pumped through this electrolyzer, which is absent with electricity, and the ion exchange happens with a byproduct of hydrogen. So what you're going to see is a bunch of bubbling up hydrogen that's off-gassed, and it's diluted with air and blown out the top of the facility. It sounds dangerous, hydrogen, but it's not. There are a lot of safety mechanisms that don't allow it to run if there were any kind of concentration that would be dangerous. And really, even though you'll see it looks like there are a lot of bubbles in there, there's a lot of gas, it's really not enough to even capture to, power for a vehicle or anything like that, or generate electricity off of. So it's not something we can capture and maybe use to generate electricity later. But anyway, so let's go in and take a look, and if you have any questions about that afterwards, we can answer. All right, so this is our generator here. Water or brine solution is flowing from the salt tanks up through the bottom and going through these metal plates here that have electricity flowing through. Inside here is where the exchange is taking place, and you can see the bubbles coming off of here is the hydrogen that's escaping. The liquid that's above here is sodium hypochlorite or bleach at 0.8% strength, and it's flowing up and going to a tank over here, which is our product that we use to disinfect. This whole process here takes about 3 pounds of salt, 1.8 kilowatts to make 1 pound of chlorine. After this process over here, it goes into the production tanks. We have a metering pump system that will meter it out at a specified dosage that the operator determines. So this is the bleach. So we go through a whole tank, but we switch tanks every day. We use the middle part of the volume of the tank because it's easier on the tanks. The deeper you cycle the tanks, the more stress it puts on them. So we only use about the middle third of the tank. We'll move to the next tank, and then it will generate new bleach into this tank after we switch tanks. These metering pumps will dose whatever the operator determines is necessary for disinfection. We go off a residual in our water. So we want to maintain a 0.7 residual of chlorine. And so he'll make adjustments, or she'll make adjustments to this pump to make sure we're getting that 0.7 at the reservoir out back. All right, so we're here in EWEB's new water quality lab. We just moved in here last week. We started doing analysis. Still waiting for some equipment. There's a few little items that aren't finished up yet, but it's operational. So I'm going to kind of head around and maybe look at some of our equipment here, explain what we might be getting. A departure from the past is that we're bringing in a lot more equipment that we used to send out analysis for. So we're going to be having a atomic absorption metals analysis. We're going to be doing our own total organic carbon and dissolved organic carbon. And this last year we got our own hazardous algae toxin machine, or Abraxas, which does the ELISA method for analyzing toxins. And we've been certified by the state on that piece of equipment, so we can do our own toxin analysis. And that's really important for us, because we've had, in 2018, we of course had a bloom in cougar that made us start changing some of our treatment here. We started using, once again, the powder activated carbon. And since then, we've been hypersensitive to that, because of course what happened in Salem in 2018, you know, they had a do not drink order. And so we're trying to be proactive in our testing and in our treatment processes around that. So some of the other analysis we do in here, we do benchtop UV 254 analysis, the alkalinities and hardness. We do conductivity meter. We have a couple of spectrophotometers, so we can do different wavelength, whether it's color or a lot of other constituents. I mean, there are some methods for metals in here too, like iron. We can do our own nitrogen nutrients. We do the phosphorus and orthophosphorus. So these are all kind of new methods that we've gotten just in the last few years. We didn't really do a lot of that wet chem before. It was mainly the microbiology. And then moving around here, you know, we have our balances and our dishes for doing our solids tests. And then in the back of the room here is where the Abraxas ELISA method machine is. So this is really a robotic instrument where this arm moves and puts in to different vials chemicals, and there's different wait times for reactions to happen. We had initially got a more manual method that was much cheaper, but we found that it was so hard to duplicate and replicate over so many samples that we couldn't even get certified by the state using that equipment. So we went and got the more automated version, and since then have been able to get certified by ORLAP. The missing equipment that we're going to have here is the TOC and DOC. The DOC, of course, is just really a filtered method for dissolved organic carbon. And then the atomic absorption equipment will be here. That's what the ventilation is for. So we'll be able to do our own metals. I think the first analysis that we're going to try to do is our lead and copper analysis, and then maybe some of these other ones that we're seeing in our system, like the aluminum that we just spoke about earlier. We'll probably be looking at those methods. The main methods that we have been doing here all along for better than 60 years, I think, are the microbiology. Heterotrophic plate count is one of the ones that's been going on the longest. And so we go around through our system. Operator goes out, gets about 25 samples on a route through town, and brings them back, and then we analyze them for bacteria, and we also do a coliform and E. coli testing on those. So we have several routes. We have 100 sample stations around the city. We need to deliver about 160 samples to the state every month to prove that our water is safe all around town. Do you have any questions? Right, so the McKenzie River really is a pristine source of water, and it's not just the spring water. It's also it's protected in a way that there are no, wastewater outfalls upstream, and so the main constituent for us here is just regular old E. coli. In any water source, you have, like you were talking about, runoff from agriculture, or even just normal waste streams from a forest. So those in the summertime especially, you have those increased coliforms and E. coli. Those are our main concern. So, chlorine is our big weapon for that, and that's doing all the heavy lifting. We do test for the pharmaceuticals. We haven't had any that are even remotely close to any maximum contaminant levels. A lot of them are non-detects. We do have a really good septic system program that's been in place for over 10 years now, I think, where we help homeowners in our watershed that have failing septic systems to get loans or grants to replace those septic systems. And our source protection folks have proven over the years that our water has actually improved from doing that. But again, very minuscule amounts of those sources. I think the main unique part of this is that our pristine source allows us to have a really low-tech method of treatment. And so we have what you call a direct filtration plant. So you saw the basins that I had pointed out earlier where the settling takes place. In a conventional treatment plant, you would have plates and mixers that would facilitate the falling out of that material into the basin. But because we have such a good water source with low organics, we don't even need that. So it's very low tech, very low cost. So I would expect, of course, the more polluted your water is, the more high tech, the more money you spend on cleaning it. So I would expect other places to actually be quite a bit different than here. Well, we have a big system, so having a second source, if you think of it as, so you're filling a pool with water and you're putting in with two different sources, it's not quite the same. You're not going to get that mix of water. It's not going to just all mix together nice. So you have a piping system. You put in a second plant, you might actually only push out water from that plant a certain distance into the piping system, and the plant and the water from this plant would push out a certain distance. So in that way, it wouldn't affect all customers, and so it's hard to say really whether there would be any significant changes. The Willamette River is a very good source still for all the bad publicity that it gets. If you go around the country, I'm sure there's hundreds of millions of people even that would love to have a source as good as the Willamette at this stage of the Willamette. It's not the Willamette in Portland, it's the Willamette here in Southern Oregon. So, well, the plans that we had, we did a 30% design for a facility 5 years ago, and the plans for that facility were to make a really resilient earthquake-proof plant that could be put would be able to go back in service within 24 hours. So you take, but that costs a lot of money. So you have these orders of magnitude, and you have this develop these service level goals about, you know, how quickly do you want to get back in service from an event that's a wildfire or an earthquake, and so you make those kind of determinations. The design we did previously was for an earthquake resilient plant. I think we're going to go back into a design mode, so I'm not for certain what that will look like, but that's where we went before. We don't really face a lot of contaminants in the distribution system. One of the great things about putting our biofiltration in a few years ago is that we're growing that microbiology up here before we were sending it through the filters to the system, and it would manifest itself as biofilms in pipes and maybe cause a taste and odor issue in parts of town that might have dead ends or low flow through that part of town. So by doing that, you know, our system's going to gradually get better. So you know, the taste and odor issues are going to get better. We don't have a lot anyways, but also what happens is, because that bioslime is not growing in the system, we can use less chlorine, because it would be using up chlorine in the distribution system. So it makes the residual last longer, keeps the water fresher. So I think we're kind of addressing, you know, our water age issues and those kind of things already, but there aren't any really big gotchas in our system.
So we're here in our pilot filter room. I spoke earlier about our biofiltration project. I wanted to point out our new, or not our new, but our test pilot here that we started working on with the University of Toronto. The testing we did in this was some new testing for biofiltration that tried to help us understand, when we shut down a filter for extended periods, how did that affect the biology in the filter? And so we did different shutdown lengths and then measured the biological activity in the filters, checked the enzymes levels in the filters, which can tell us how active the bacteria are, if there's a lot of enzyme activity. So what we're going to be doing in the next test here is we'll be adding some more filter media on top of this here, and we'll be checking to see if the biological community is happier in that media. Also, what we started last year is we started getting toxin samples from lakes that were having toxin blooms around this area. And we put it through our pilot filters to understand how the biological activity would treat that toxin. We did about 4 runs this last year on it, and I think we're just now getting down to where we have a process that works. So it's really kind of a difficult thing to get that toxin diluted to a value that's known, and then test the treatment process. So we spent last year getting our method down, and hopefully this year we'll be able to actually get some real results.
All right, so we're here back out front in the lobby with the pilot filters, and so the pilot filters are not just a fun testing mechanism for new projects. They're also a real important part of our tools we use here at the facility to operate. And so these are representations of the large filters in the back, scaled down version. And the primary function is operators test the dosing of coagulant, aluminum sulfate, and they will determine what dose works best as far as removing turbidity using these filters. And that's important because it takes about 6 hours this time of year for the water to get back to the real filters. So if your dosing isn't correct, then it really can mess up your whole plant. So the water comes through here after about 20 minutes. So it's a snapshot of what is going to be happening 6 hours later in the back of the facility. So that's what's going on here. It's a really important tool, especially during turbidity events, to be able to react to different river conditions quickly before it gets to the rear of the facility. So we monitor pressure at the top of the filter and the bottom. That tells us when they're clogged. So as the pressure increases, we measure it in inches on these filters and in feet on the large filters, which is feet of water column. When it gets to a certain height, then it's time to backwash the filter, which essentially reverses the direction of the water, expands the media, releases all of the dirt and materials and flushes them out. And then it will re-stratify the media back down again. So I'm going to try to show you that here. It's been a while since I operated this, so check it out. So right now it's opening up valves, and it's going to start reversing water flow from the bottom. You can see it expand. Well, it looks like they must have washed this filter since I took a look at the screen and missed it, but usually what you would see is a bunch of brown coffee colored dirt coming up out of here, but it looks like they washed it while I was out of the room. So I washed the wrong one, but at any rate, this is the process. So got a ladybug taking a ride on there. So in our large filters that we'll be looking at in the back, they can run anywhere from 24 to 72 hours. And really the longer runs are happening during cold weather, clear water conditions. So usually springtime are the best conditions where we get really long filter runs. So the different specific gravity for each type of media makes it so when it's stratifying, they all fall back into place. So the sand will end up on the bottom, and the anthracite coal will end up on the top. Some treatment facilities have three medias. They might have like a garnet, which will be on the bottom. It's kind of a red colored garnet that we used to use here, maybe an inch on the bottom. That helps out straining materials that are smaller, but it also makes the filter run last, or shorter, I should say, rather than lasting longer. And that's the process. All right, so here we are at the sedimentation basins. If you remember before, we had discussed adding some chemicals out in the front yard, and one of them was aluminum sulfate. So that's been added, and then at the base of the sedimentation basin here, a cationic polymer is also added. And in this area, it does some mixing, starts developing those long chains with the cationic polymer and the coagulant aid, and then things drop out into this basin. You can see how dark the water is here. That's from the powder activated carbon. Have some floating materials. That's just alum and coagulant aid that's kind of just floating along with algae. So you can see this stilling portion here where it hits the perforated walls is going to be a little bit darker, a little bit browner than it is on the other side of the wall over here. So you're getting a lot of things drop out right here and then gradually across the basin. All right, so here we're at our filters in the back. Proceeding back here, the water, maybe just the top 10 inches of the whole 16-foot deep basin makes it into this filter, so a lot of it is decant essentially. And then we add some filter aid polymer at the beginning of the filter here that helps the filter ripen when we first put it on so that it traps more of the particles. So in here, while this filter is running, we're monitoring turbidity, head loss to see how fast it's clogging. We're monitoring flow through the filter, and also the level of the filter is monitored in here for when we're doing automated backwashing. All of the valves that are used here are automated and are connected to a HMI system that we'll take a look at when we go inside. So we have a system that operates the filters separately from the SCADA system at this time. So essentially two SCADA systems. And then all of these mechanisms help the operator make decisions on when to stop filtering. So as I stated earlier, our peak this last year was about 48, 50 million gallons, and we're rated for 88 million gallons. The most we've ever done in a day is 71 million gallons, and that was in the 90s. So we have had quite a diminishing demand through the recession. And part of it was due to recession, and part of it was due to conservation. And so we went from an average of maybe 62, 63 million peak demand down to below 50. And we really haven't come back. So we're just inching up every year. So we really have a lot of excess capacity here at this treatment plant. And a second source would not necessarily be needed for capacity just by itself. It's more about resiliency and redundancy. All right, we're in our rear control room here at the treatment plant. So we have a lot of controls at our fingertips here. Our SCADA system allows us to operate all of the equipment at the plant from centralized locations. We can operate this from a front and rear control room, or essentially from any laptop or PC station here at the facility. The operator has a regiment of hourly readings that they do. So we have two control rooms. The one in the front, they take readings with water quality analysis, where they check the chlorine and pH of every different process step during the facility. And then here in the back is where we do the monitoring of the filters. So they're entering things in here from SCADA and from observations every hour. It used to be a regulatory requirement now most of those regulatory requirements are automated. So now it's more of a keeping the operator engaged in what's happening at the facility, is why we keep doing that. So along with all these operational controls that we have, we also have a historian which tracks all the devices in our facility, collects data, allows us to troubleshoot equipment. We even have our lab analysis in with that, so we can track changes in water quality as they go through the facility, and we have that history that we can look back on. We're going to be integrating the source water analysis into that. We've already done the distribution system analysis, so I'm anticipating by the end of this year we'll be able to have a source to tap water quality analysis, and we'll be able to track that water, all the way from the top of the McKenzie to your tap, essentially, for water quality. All right, so here we are looking out back at our 15 million gallon reservoir. At the beginning of this reservoir is where we're adding our disinfectant, and we're getting most of our contact time to kill all of the E. coli, coliforms, other organisms that are in there. So this is where all the really important work gets done as far as chemically. We do our pH adjustment at the beginning of this reservoir as well to 7.9, and the reason that is so high is it's been optimized for lead and copper. I talked a little bit earlier about how you should flush out your tap at home, and so part of what we do to help with that is keep our pH at a certain level so that lead does not leach out of pipes, and we test that every 3 years. We come through with the lead or copper testing, we're by regulation, and we haven't had any hits of any concern the last time, and we appear to be getting better as time goes on, essentially, because we're running tighter controls on our pH. The mechanisms for and the monitorization to keep those things steady and constant have gotten better. So all of those things help with that lead and copper. Then after this reservoir, we have the pump station on the end where we have the 7 pumps, and you can see the transmission mains kind of run right down the valley there, and you can see Autzen Stadium off in the distance there. That's kind of the track it takes to I-5 where we hit the monitoring station. What changed here in the last year was our gas chlorine system was right over here in this building, and just to kind of illustrate, the safety aspect of that is chlorine gas is heavier than air, so if there was a release, it would seek out all the low areas, right? And as you can see, we have a community right below us. So we used to have a SENS program that would send out an alert if something should happen and call the folks in this neighborhood for shelter in place and that kind of thing. So that's a big aspect of the change that we made too, is just the safety factor.